Imagine stepping into the inner world of a generative AI. It's a realm far removed from our everyday experiences, a landscape built of pure information and mathematical relationships. When we ask it to conjure up a cat that's never existed before, a feline unique in all the world, it's not simply grabbing bits and pieces from old images and stitching them together. It's embarking on a journey, navigating a hidden landscape, a complex terrain of interconnected information. This landscape isn't a random jumble. It's a highly structured space, carefully organized and meticulously arranged. It's not a chaotic, disorganized list of isolated facts, scattered without rhyme or reason, but a continuous, flowing surface, what we call a neural manifold. Think of it as a geometric map, a carefully constructed representation of all possible cats, every conceivable feline form, faces, every nuance of human expression or musical styles, from classical symphonies to modern electronic beats, where the subtle difference between a tabby and a Siamese, two distinct breeds, is a precisely measurable distance within this space. Understanding this fundamental concept, grasping the nature of this space, is like holding a key, unlocking the secrets to the inner workings of the mind of the machine. To truly grasp the immense power of generative AI, to understand its potential, we must venture into and explore these high-dimensional spaces, these complex mathematical realms, and cultivate a geometric intuition, a sense for how these spaces are structured and how they behave. AI learning isn't just about blindly adjusting numbers and tweaking parameters, it's about carefully sculpting data, shaping it with precision into elegant lower-dimensional structures, simplifying the representation while preserving the essence. The neural manifold acts as a distiller, extracting and refining the essence of data, capturing its most important features, highlighting the key relationships, and preserving the underlying structure. Let's peel back the layers one by one and see how raw, unprocessed data in its original, unrefined form, like millions upon millions of individual pixels, each a tiny piece of information, ultimately becomes a coherent generative map, a structured representation capable of creating new content. This map isn't just a passive storage container, a simple repository for information, it's a dynamic landscape of pure potential, a space brimming with possibilities, where new ideas are born, where innovation takes flight, and where creativity knows no bounds. So, what is a neural manifold, really? What does it mean for the future of AI? A manifold is a simple but powerful idea. It's a concept that bridges the gap between the familiar and the complex, allowing us to understand high-dimensional spaces through local approximations. Imagine the Earth, globally a sphere, a curved surface in three-dimensional space. But locally, right where you're standing, it feels flat. You can walk around, build a house, and for all practical purposes, treat the ground as a flat plane. A manifold is any space that up close looks familiar. It's a space that can be described by a flat, Euclidean space in a small enough neighborhood around any point. Like a flat plane, a two-dimensional surface that extends infinitely in all directions. This local flatness is the key to understanding manifolds, even if it's curved in higher dimensions. The curvature is a global property, but locally it's always flat. This allows us to use the tools of calculus and linear algebra to analyze these complex spaces. Now think about data. Data isn't just numbers, it represents information, patterns, and relationships. A 100 x 100 pixel image is a point in a 10,000 dimensional space. Each pixel's brightness value becomes a coordinate in this high-dimensional space. Most points in this space are meaningless noise, random arrangements of pixels that don't resemble anything recognizable, but real images cluster together on a tiny, intricate surface, a manifold. This manifold represents the underlying structure of the data. This manifold is where all plausible images live, the set of all possible images that could realistically exist, with each point representing a realistic variation. Small movements along the manifold correspond to subtle changes in the image. For example, the manifold of cat images is a surface where every point is a plausible cat. It captures the essence of catness. Nearby points are similar cats, perhaps the same cat in slightly different poses or lighting conditions. Distant points are different breeds. A Persian cat is far from a Siamese cat on this manifold. Far-off points are just noise. They are pixel arrangements that don't resemble any cat or any recognizable object at all. The neural network's goal is to discover and map this hidden manifold. It's trying to learn the underlying structure of the data. It learns the structure of meaningful data, identifying the patterns and relationships that define the manifold. ignoring the vast emptiness of random possibilities. It focuses on the regions of the high-dimensional space where meaningful data resides. The manifold has a much lower intrinsic dimension than the space it inhabits. The cat image manifold, for example, is likely far less than 10,000 dimensional. This is how AI finds order in chaos, by identifying the underlying structure within seemingly random data. By mapping the surface where real data lives, it's creating a representation of the data that captures its essential features. The manifold is the foundation for generative creativity. It provides a framework for creating new data points that are similar to existing ones. Understanding it lets us see how AI can create, not just copy. By navigating the manifold, AI can generate novel and realistic data. The next step: how does AI find and use this manifold? How do neural networks learn to navigate these complex, high-dimensional spaces? Neural networks find the manifold through intelligent compression, using an encoder. The encoder maps high-dimensional data, like a 10,000 pixel image, into a much smaller set of numbers, a latent vector. This latent space holds the essential attributes of the data, discovered automatically by the network. For faces, one dimension might represent a smile, another glasses, another hair color. Similar images are mapped to nearby points. Very different images are far apart. The encoder flattens the tangled data into a neat, lower-dimensional surface, the neural manifold. This is dimensionality reduction, turning a crumpled paper into a smooth map. Every image becomes a single point on this map, translating pixels into geometry. The network has learned the language of latent space. Learning the manifold is a gradual sculpting process. At first, the encoder's mappings are random, creating a chaotic cloud in latent space. Enter the decoder. It reconstructs images from latent vectors, forming an autoencoder. The system is trained so the output matches the input, forcing efficient compression. Like describing an object in a few words, the network learns to focus on essentials. Through millions of examples, it refines its map, pushing similar points together and smoothing transitions. Small moves in latent space yield small, realistic changes in output. The chaotic cloud becomes a smooth, organized manifold. The geometry of latent space now mirrors real-world structure. This is how AI sculpts meaning from data. Once the manifold is learned, after the AI has successfully mapped the data's underlying structure, the decoder becomes a generative engine, a powerful tool capable of producing novel outputs. It's like a factory that can churn out an infinite number of variations based on the learned patterns. By picking any point on the manifold, by simply selecting a coordinate within this organized space, the decoder can create a new, realistic image. It translates that abstract point into a tangible, visually coherent representation. This is how AI generates. This is the fundamental mechanism behind the magic, not by copying. It's not simply regurgitating existing data, but by sampling from its learned map, by intelligently navigating the relationships it has discovered. The manifold's smoothness allows for more than random sampling. Because the space is continuous, we can do more than just pick points at random. We can interpolate, trace a line between 2 points, smoothly transitioning from one location in the latent space to another, like a young face and old face, and generate a seamless transformation. We can create a smooth animation of aging, revealing the subtle changes in facial features over time. This is the power of the manifold, meaningful, continuous change. It allows us to explore the spectrum of possibilities in a fluid and intuitive way. Sampling is like improvising music within a scale. The manifold provides the rules, it sets the boundaries and defines the relationships, and we create new melodies. We explore the possibilities within those rules to create something unique. By exploring latent space, we explore the full range of the data's possibilities. We can uncover hidden variations and unexpected combinations. We can find averages, create caricatures, or invent entirely new forms. The manifold is a landscape of creative potential. It's a space where imagination can run wild, guided by the underlying structure of the data. This is the heart of generative AI. This is the engine that drives the creation of new and exciting content. Neural manifolds power real-world applications. Style transfer combines the content of one image with the style of another thanks to the manifold's separation of what and how. Interpolating in latent space enables smooth morphing and data augmentation, creating endless variations for training. Anomaly detection becomes possible. If a new data point falls far from the learned manifold, it's flagged as unusual, vital for quality control and fraud detection. In medicine, a scan that doesn't fit the normal manifold signals a potential problem. In finance, outlier transactions are instantly identified. The geometry of latent space defines normality and flags anything that breaks the pattern. Manifolds turn abstract math into practical power. The future of AI is geometric. Neural manifolds let us see inside the black box, revealing how AI organizes knowledge. Geometry gives us tools to control, interpret, and ensure fairness in AI systems. By understanding the shape of data, we can identify and correct bias, making AI more transparent. Manifold learning applies to images, language, sound, and beyond. Next-generation models will learn even richer geometric structures, enabling new forms of creativity and understanding. Studying manifolds is about understanding how meaning takes shape in machines. The journey into these hidden spaces is just beginning. Don't forget to subscribe to our YouTube channel for more insightful content.